So I'm going to talk about using GPUs with Python. And I will just move this here. First, before I start talking about using GPUs with Python, I just want to be sure that everyone updated the tarball. I am also going to update it here. So I'm downloading a new copy of it. Okay, so using GPUs with Python. What is GPU acceleration? How to enable GPUs in Python code, for example, with CUDA, how to deploy GPUs at the various centers. That is things people might wonder about. So here I'm going to do a short intro about GPU and GPU code acceleration, and talk a bit about the GPU nodes at the centers, and then show how to make a batch script asking for GPU nodes at HPC2N, UPPMAX, LUNARC, and NSC. I'm not going to cover PDC in that matter because, well, I can show how you ask for the GPUs, but my examples didn't work as they should because, as you know, PDC has AMD GPUs, Cray, and the number version that you can install with pip is not really compatible with the ROCm that is there, and I then tried to use HIP, and HIP Python would not install correctly, so there are compatibility issues. I'm going to figure out what they are, but not right now. So I'm going to leave out PDC for the examples because of that. So first, introduction. In order to understand what a GPU is and what it can, it's worth it to compare it to pure CPU. And here is a schematic of a CPU. This is an L40. This is a Zen 4 AMD CPU at the SPC2N. This has 256 cores. It is divided into two NUMA nodes. So physically, these cores are sitting on two NUMA nodes. And each of them has, each core has their own cache memory, as you can see here. And there's also shared cache between blocks of cores. And then each of these NUMA nodes has also shared memory. In addition, there is connections from it to the local disk, and it is physically connected to this NUMA node, which means it's slightly slower from the other one. It's not much. Then the Ethernet connection is sitting on this NUMA node. Another I/O Open Fabrics is their version of InfiniBand. If you know about that, it is simply a fast interconnect. So, and this is how a typical CPU node might look, with lots of cores. This one 256, but we have between 28 and I don't remember, more than 256 cores at least. So so this is a typical CPU node. Base frequency is 2.25 gigahertz, but it can boost higher up to above 3 gigahertz. If you're looking instead of GPU architecture, a GPU card of the type Ada Lovelace, like the L40Ss are, would look like this. And here you can see it has a lot more cores. Actually, each one of these small green ones, there are several in each here, is a CUDA core. And then there are also tensor cores, which I believe are the blue ones. And then there are in this one also ray tracing cores, which are the yellow ones. And here is a zoom in of it, of each one of these uh, same slots here. So you can see here how it looks. Each one here, these are the CUDA cores. And there is a lot more of them than, so you have a lot more cores than you have on the CPU, but each of the cores are slower. And here is how it might be connected. So this is the CPU, and each of these CPU NUMA nodes, the CPU blocks here, are each connected to a GPU. So there's two GPUs on this type of GPU node. So you still have the CPUs, so you can use also, so you can do hybrid calculations, and then you have the GPU card, one on each of the NUMA nodes. Some of the nodes have more, some that have 6 GPUs, some have even more than that, but this is an example. So you can see that in this case, you would have access to both CPUs and GPUs. So imagine that this thing here, it looks like what you have up here, each of them. So differences between CPU and GPU is you can look at latency, you can look at throughput. Latency is the time spent in one computation. Throughput is the number of computations. And when you look at that, you can say CPUs has a low latency. It can do fast computations. The GPU does them slower, but it has low throughput. There's only a few computations simultaneously. So the GPU has lots of cores that are working slower, but there are so many of them that together they are working faster in some types of calculations. So you can look at it like this. The CPU, you have a road with cars that are going fast, but there are not so many of them. And the GPU has a wider road. It has more cores, and they are going slower, but there are many of them. So that is how you can look at latency and throughput here. And as you can imagine, not all Python programs or programs in general are suitable for GPU accelerations. Since these GPU, they will process simple functions fast. And if you have some repetitive, highly parallel computing tasks, then it would be great to throw that at the GPU. Originally, they were designed to render high resolution images and video concurrency and to do that fast. But you can also use them for any other things that requires parallel operations on multiple sets of data. So there are many other non-graphical tasks where they work for also. And they are commonly used for machine learning and also scientific computations, where you can take advantage of this massive parallelism. So when we look at Python, many of the Python packages are not CUDA aware or aware of other GPUs because GPUs are not all NVIDIA's that can use CUDA. They're also AMD GPUs. But some of these Python packages have been written specifically with GPUs in mind. And if you were, for instance, working with NumPy and SciPy, you would you could optimize your code for GPUs by using CuPy, which mimics many of the NumPy function, or you can use Numba, which Pedro also mentioned, which has bindings to CUDA and will let you write CUDA kernels in Python yourself. And that means you can use custom algorithms. One of the most common uses of GPUs is with Python is for machine learning or deep learning. And in those cases, you will use TensorFlow or PyTorch libraries that are made to handle both CPU and GPU processing internally without you having to do anything with that. And that will be mentioned more later today when we talk about machine learning. So GPUs at the various centers. Well, when you log into the center, you will get to a login node, and usually that will not have GPUs, or if it does, it's not something you can use for computations. So if you need to use the GPUs, you will need to launch an interactive job, as you have seen earlier, or to submit a batch job, as you also have seen earlier. So at UPPMAX, Rackham, which is the computer we have been using at UPPMAX, they don't have GPUs on Rackham, but they have on Snowy. And on Snowy, you can use this module here, which is quite useful because that has some machine learning packages for Python that are made for GPUs. There is a matching one for CPUs on Rackham itself. Snowy has NVIDIA T4s, and in order to access them, you need to use this batch command. And this first line here tells it to use Snowy, and the second one tells it to use GPUs, and the GPUs, this X should actually be 1 because that is only option there right now. And at UPPMAX, it will change from Rackham and Snowy to Pelle and Maya soon. And I believe it will be Maya that has GPUs, or will Pelle also have GPUs? Can someone from UPPMAX enlighten me on that? Otherwise, well, it will be announced the system soon. So HPC2N. HPC2N's GPU nodes are a separate resource. That means that if you are asking for time on Kebnekaise, then you just ask for time on the resource Kebnekaise, you don't get the GPUs. You also have to ask for time on the resource Kebnekaise GPU. The regular compute nodes don't have GPUs, but Kebnekaise has many different types of GPUs. As you can see, there are V100s, A40s, A6000s, L40Ss, A100s, H100s, and MI100s. And it is worth noticing also that there are different number of cards on them. And this one is not an NVIDIA one, it's an AMD one. In any case, in order to access these cards or these GPUs, you would need to use this command here. And this batch minus minus GPUs equal the number of GPU cards you want. You can just use that command, but if you do that, then you cannot ask for more than 2 because you will not know which type of GPU you get, and so you shouldn't ask for more cards than are on the one that has the fewest. If you want to run on a specific one, there are ways to ask for only to run on NVIDIA ones, or there are ways to ask for other specific things like what type of precision they have, or if they're good for AI and things like this. But otherwise, what you can do is simply say, I want this many GPUs, and then you also add this here, which is you are specifying which type of GPU you want as well. And type can be any one of these. The L40Ss are the one, and the V100s are the ones we have most of. There's more information at HPC2N's guide to the different parts of the batch system. LUNARC. LUNARC has NVIDIA A100 GPUs and NVIDIA A40 GPUs, but the latter ones are reserved for interactive graphics works on the on-demand system, and Slurm jobs should not be submitted to them. And if you do, you may have your jobs cancelled, so don't do that. So in order to use A100 GPUs on Cosmos, you add these two lines here to your batch script. First, you say, I want to run in the partition that has the A100s. And then you say how many you want. And you can only choose one, I believe, here. There is also another option that is to use the GPUs that are on the Intel nodes. And there you can get one or two. But there are fewer of these, so this will be more likely to get you something fast. NSC, that is Tetralit in our case here, has NVIDIA T4 GPUs. In order to access them, add these lines to your batch script or interactive jobs. And you need actually these two lines as well. It is something that they require for this, even if though this is for the CPUs. But this line here tells that you want one GPU for each of the tasks. So PDC. PDC Dardel is a Cray. It has AMD GPUs and it has these MI 250X and 2 gig GPU cards per node. And in order to access them, you add this to your batch script. So you say, I want the entire node and only one task for the node. And then you say, I want the partition with GPUs. And when you do that, you will get access to these GPUs. Okay, so I have a number example, and number is installed on some of the centers as a module, HPC2N and LUNARC, and in UPPMAX, it's part of the Python ML packages GPU. On NSC, there is a number version available as a module. It is a very old version. Because of this, you can use a virtual environment, and this line is wrong. We didn't create it today. It is something we did in the previous version of the course, and I forgot to change this line. PDC, Dardel, has AMD GPUs, as I mentioned before. I could not get the version of number that is compatible with CUDA. It does something with ROCm in order to actually use number on AMD GPUs, but no version after 0.53.1 has compatibility, and yet that one is too old to work with anything else installed. There is the option to use HIP examples. That requires you to get HIP Python installed in the virtual environment. I tried doing that. There were also problems with this, at least getting it to run, but there are some examples you can play with. But otherwise, I suggest for now, use these 4 other systems. So here is a Python example, add list p, and it will be available in the tarball on the exercises that you downloaded. It's inside exercises and programs. It is somewhere here. And that is the script, the Python script that we're going to use in this example. And we need either a batch script or a interactive job. So I would suggest that we now try and type along. So everyone go to the terminal window or ThinLink, wherever you are working. Go to the directory with the exercises. I will do that also here at HPC2N. So at each center, there should be a directory for each of the centers. So here at this system, I am on Cosmos, so I will go to the LUNARC directory. Here I am at HPC2N, so I will go to the HPC2N directory. And I have been logged out of UPPMAX. I will go to that here. And then I needed to get the tarball, see what it was called. This one here. Not there. I want to go to my own directory first. And then I am untarring it. And actually, I will just move it here for a little while, and then I will first start this example here for LUNARC. And I just want to say something about it here. First, there's this shebang here I talked about earlier. And then there is the project ID. I'm asking for 5 minutes. I'm gambling it's not taking longer to run it. And then I am also asking for this GPU partition here and one GPU. Then I'm loading modules. At LUNARC, you have Numba available, and I'm loading these other things because I also need SciPy and NumPy and other things. So I'm loading this, and then I'm running it with Python. So what I'm going to do here is that I am first looking in the directory and at the shell script, and here at the LUNARC, sorry, I am again using VI. I should use Nano. I go to this path here that I want to be so that I can access the programs directory. And in order to do that, I need to know what my path is. And this is the path. So I need the the thing is LUNARC doesn't have a storage directory. You're using your home directory. So make sure that you actually copy that path instead. So if you simply put it in your home directory, then just copy that. Then let's go in here again, go down to my path. I am removing this path here because we don't have a storage directory. And we are just tarball. And then I'm adding in the link that I just, the rest of the path here. So I have it in my home directory. It's a tarball I unpacked. It's in this directory here, the programs. So here, if you just put it in your home directory, you would just change this to your username at LUNARC. Okay, this is now safe. I will save it. Yes. And then I will submit it. While that runs, I will do the same thing at HPC2N. I will do this here to see that here I actually have a path to a storage directory, and the name of the directory I created is this one here. And I cloned it so it looks like this. I will open the file here as well. and make changes to it. Now, if you're in the storage directory at ASP.C2N, this first path here, leave that. Then change this here to whatever name you created or directory. I cannot remember to use nano. I apologize. Remove this here and put whatever name you gave your directory in the storage directory. If you cloned it, then if you did git clone, it will be in the ASP.C Python here. If you took with wget the tarball, it will just be exercises, examples, programs. I'm saving it. And also submitting that. Now, let's try and do this interactively as well. So I have an example here for how to do that at the UPPMAX. I'm simply going to copy this line here and place it here, and then I will start it. So we can see how it looks interactively also. So now I am on this compute node at UPPMAX, and I am in the directory UPPMAX, but since I am going to run this interactively, I'm actually going to instead go to the programs directory, and there I have this file here, add list p. So let's run it first, of course. I should not forget. I also need the there, I can scroll. I need the modules, so I will copy those. So I'm doing that. And now I can run my script that uses number like this. And it will take a little while. And while that runs, I am going to check if this has finished. It has. Slurm out. Let's look at it. It ran. It says running on CPU. It took 19.74 seconds. On GPUs. That part took 0.26 seconds. Let's see if it also finished at the ASP.C2N, and it did. So I will again check. And here, the CPU, it took 14.56 seconds, and the GPU 0.36 seconds. So the CPU was faster, the GPU not so much. Now it ran at UPPMAX. Here the CPU took 35.41 seconds and the GPU 0.86 seconds. So this is older CPUs and older GPUs and thus took longer. Okay. But I hope that you got it to run at one of the centers at least, because now it is time for exercises. And in the exercises, I should probably also just mention what happens at the NSC at Tetralit, but it is very much the same as the other centers. The only difference here is I will go into it here to the directory, into NSC, and then I will open this batch script. Here I need to change my path again. And it is like the other places, this directory here, change it to whatever you named it. If you have a tarball, delete ASP.C minus Python. If you cloned it, leave it there. That is the only changes you need to do. Then you can submit this as it is. So this example here, the 2D integration program, it looks with CUDA support for number. It looks like this here. You can see it uses not just number, but also NumPy. And you can try and run that as part of the exercise. And then you can see also here that the large size of the grid compared to the serial case that I didn't run here, but the grid is quite large. And in order to run it faster, we can take advantage of shared memory. And that means that there is another example here. And you can try run that as well and see what the difference is. And actually, you can run both of them in the same batch script, and then you can compare the timings of them. And there are examples for how it would look. But try use the example from the add list.sh, the shell script there, and see if you can modify it to run these two programs instead. And there should be minimal changes that needs to be done. And you should be able to run it at least these 4 centers here. So the thing to mention here is you can deploy GPU nodes with Slurm, either interactively or batch. And it's very good to use the number package, but many other Python packages as well are made for using the GPUs, and you will see some of them in the machine learning section. Of course, if you run interactively, you could also do it from inside Jupyter, VS Code, or Spider. And CUDA doesn't work directly on AMD GPUs. And there's more GPUs in the machine learning section, and there is some additional information here. We have 10 minutes, and in that time, I would like you to try and get these 2 programs to run on your preferred center. So let's take 10 minutes for exercises.